Okay, so we're recording now. All right, so let's get started. So what chapter do we want to start with? Chapter 10. Okay, let's do 10. Then we'll work our way back. What is question 13? Yeah, so let's do some new stuff first. All right. Also, I suggest if you downloaded the packet earlier, re-download it, because I had to make some changes to it, because there's some things that are no longer learning objectives, and I deleted those from this packet. Okay, so yeah, let's do chapter 10. So chapter 10 was gases. It's the kind of the last time that we have to use our calculators in this course, because we introduced the idea of the ideal gas law, PV equals nRT, where if we have pressure, volume, temperature data of a gas sample, we can figure out how much gas we have. What is that N? What's this N variable? What does that stand for? Moles, yeah, and so now we're introducing moles again. So remember we talked about moles in stoichiometry, where we used molar mass, molarities. We have this new way to play around with moles, but specifically we're talking about moles of a gas. So let's work through these problems. So chapter 10, we have a high altitude balloon, and it has this volume at this temperature and pressure. What is the volume of the balloon at 20 kilometers high, where the temperature is this temperature and that pressure? So it sounds like we are solving for a volume. And so how we approach this question is we recognize, so see how I highlighted this in different colors, that we have one set of volume, temperature, pressure data, and we're given new temperature and pressure data. So we have a sample that's undergoing some type of just condition changes, that its temperature or pressure or volume is changing, but we're taking that same sample and we're just changing where it is. So we're not actually going to use the ideal gas law yet. We're actually going to use the other equation that we learned about in chapter 10, and that is the combined gas law, where we can take temperature, pressure, volume data of a sample and change where that sample is and get new pressure, temperature, volume data. So P1 times V1 over T1 equals P2 V2 over T2. So it's just up to us to put these variables and the given information into the correct spot. But what's the trick for using the combined gas law? How do we have to do our units here? We need to make sure pressures, does pressure have to be an ATM when using the combined gas law? No, what do they have to be? They just have to match. They just have to be the same. So note here how I gave it to you in ATM and torr. You just need to make them match. They can either both be ATM or both torr, it doesn't matter. Volumes also, they just need to match. But temperature, it needs to match, but that one has to have a specific unit. It can't be in Celsius. That temperature unit has to be in Kelvin. Yeah, so we're going to use the combined gas law. The variable that we're solving for here is V2, because that's what the question is asking. What's the new volume once we put it into these new conditions? And so does the supplemental information give you pressure conversions? Let's look. Let's look, because I don't remember. Does it give pressure conversions? No? No? No, it doesn't. It does not. Okay, so keep that in mind, because we need to change that atmosphere to torr or torr to atmosphere. So I know, I've memorized at this point in my life, that 1 atmosphere is equal to how many torr? 760. And a torr is the same as what other unit? Millimeters of mercury. So 760 torr, 760 millimeters mercury, it's the same thing. So this second pressure is 63.1 torr over 760, and whatever that value is the ATM value. And I think, did I write that down? It is 0.08302 atmospheres. So we just plug everything in, solve for V2. So I'll move stuff around. So P1 V1 over T2 over T1 P2 equals V2. And so plugging all those numbers in, pressure 1.01 atmosphere, that's its initial pressure. Its initial volume is that big number, 1.41 times 10 to the 4 liters, times the second temperature. Why did I make this so messy for myself? No, so messy. The new temperature, so do recognize that these temperatures are in Celsius. They should be in Kelvin. That equation is given to you where Kelvin temperature is equal to your Celsius temperature plus 273.15. And so T2 would be, I'll just do 273 plus 21 up top there. T2 is 270, or sorry, T1. No, I messed this up. That's T1. This needs to be T2. So 273 minus 48, there we go. And then our bottom T1 is 273 plus 21 degrees Celsius, divided by P2, which is that new 0.08302 ATM. And then you plug all of that in and you get a new volume, 1.31 times 10 to the 5 liters. All right, so recognize that this question, we're taking the same sample, just putting in different conditions. That's when we use the combined gas law. All right, so in the next question, let's see, do we use the combined gas law again? Gases are sold in large cylinders for laboratory use. What pressure in atmospheres will it be exerted by this much oxygen gas when stored at this temperature in this volume? All right. So it looks like we are solving for pressure. We're given an amount of oxygen gas, but it's in kilograms. We're given a temperature and a volume. So does this sample, is it changing its conditions at all? No, it's just a sample at a condition. So this is a good use of PV equals nRT, our ideal gas law, where we just want to describe one sample at one condition. So now we can use the ideal gas law. So it looks like we're solving for pressure here. We're given volume, R is a constant, we're given temperature, but we're not quite given n mole amount of stuff. But if we look closely enough, we can see, oh, I tell you that there is 2.5 kilograms of oxygen gas present. So we have to dig back deep into our pockets, back into chapter 3, where we used molar masses to convert gram amounts of stuff to mole amounts of stuff. But we got to be careful here. If I tell you that I have 2.5 kilograms of oxygen gas, what is the formula for oxygen gas? It's O2, right? Because when we need to use the molar mass, are we going to use the molar mass of oxygen, 16 grams per mole? No, we're going to use 32. Is it exactly 32? Yeah, 32 grams per mole. And that is the molar mass of oxygen gas. So let's take that 2.5 kilograms of oxygen gas and convert that into a mole amount, and we'll just insert that into our N amount that's there in PivNert. And then we can go ahead and solve for pressure. So this is in kilograms, so 1 kilogram is 1,000 grams. And then 32 grams of this sample is 1 mole of this sample, so oxygen gas. And so you can see if I have 2.5 kilograms of oxygen gas, then I actually have 78.1 moles of oxygen gas. So this is my N variable in PivNert. And then I can just go ahead and plug that into PivNert. So what am I solving for? Pressure. So pressure equals nRT over V. Now I know all of those variables. N is 78 moles, 78.1, whatever. R is a constant. Why do I never give myself enough room? Never give myself enough room. Okay. R is a constant, but which R do I use? If you look at the supplemental information, which one do I use? Do I use the 8.1 or the 0.081? 0.08, yes. So we use the 0.08206, or I guess in the supplemental information, it's 201, or 21, it rounds. And the unit of that is liter ATM mole Kelvin. And so you can tell by the unit what units of Pivnert everything has to be. Volume has to be in liters, temperature needs to be in Kelvin, and has to be in moles, pressure has to be in atmospheres, because it's easier for us to convert to those units than to memorize a bunch of different types of R. There are a lot of different types of R gas law constants based upon the unit. But again, it's easier to memorize this one. So that's R. What comes next? Temperature. So what is this? 22 degrees Celsius. So what is that? 295 Kelvin. Is it 295? Yeah, okay, good. And then volume is 40 liters, right? So probably, since all of this is multiplication, 2 sig figs is probably best here, because it's 2.5 kilograms. So the pressure here, once you plug everything in, is 47 atmospheres. And the reason pressure is in atmospheres is because the R gas law constant we're using has atmosphere within it. All right, so there's combined gas law, ideal gas law. So we also looked at gases. The idea is, when we use Pivnert, pressure, temperature, volume data of a gas, if we have, when we look at pressure, volume, temperature data of a gas, all that matters is how many particles of gas are present. That's it. Doesn't matter what kind of gas it is. I could have a mole of neon. I could have a mole of hydrogen gas. I could have a mole of nitrogen gas. As long as N is the same for all of those samples, we should still observe the same pressure, volume, temperature data. So it doesn't matter what the identity of the gas is when plugging stuff into Pivnert, as long as we have a mole amount of stuff. And so when we look at this example, we have a vessel. It has this volume, and we see that we have a mixture of gases. We have nitrogen gas, we have hydrogen gas, we have argon gas. All of these gases are inside that container. And so if we want pressure, temperature, and volume information about this sample, we need to calculate how many total moles of gas I have present. So our N total will be related to the total pressure of that gas. And so we can think about mixtures of gases in terms of total pressure or partial pressures. So nitrogen is a component of this gas sample. That nitrogen exerts a partial pressure that contributes to the total pressure. So the cool thing about the ideal gas law is we can take moles of all of the gases, get total pressure, or we can just take the moles of one of the components to get the partial pressure of that component. So this question, what do we want? What is the total pressure of the vessel? So we need to figure out what the total pressure, the total number of moles of gas that are present. So our strategy here is we need to turn all of these gram amounts into mole amounts of gas and then add those up. And that'll give us our total moles, then we can get our total pressure. Okay, so let's go ahead and do that. I try to make these easy numbers. If we use some molar masses here, nitrogen is like 28 grams per mole. Hydrogen gas is something like, I don't know, 2.016 grams per mole. And then argon on the periodic table is 39.95 grams per mole. Nitrogen is actually 28.02. And so take those gram amounts, get into mole amounts of all of these substances. So I try to make them easy numbers. So it looks like if I have 2.8 grams of nitrogen, there's actually 0.1 moles of nitrogen gas present. There is 0.2 moles of hydrogen gas present. So I'm just doing gram to mole conversions here. That's like review from chapter 3. And then finally, if I have 80 grams of argon gas, there's actually 2. moles of argon gas present. So all of these things are in my container, all of these things. So let's actually answer the second part of this question first. Which gas possesses the largest mole fraction? Meaning which gas is present in the largest amount? You can obviously see, yeah, there's 2 moles of argon and then tiny fractions of the other thing. So let me rephrase this question differently. Which gas, without even calculating it, exerts the highest partial pressure? Argon, yeah, because most of the gas sample is argon. And so if I wanted to get partial pressures, all right, if I wanted to get partial pressures of everything, I would PV equals nRT, each of these things. Each of these gases contributes a partial pressure, and we could calculate every single one. But this question, I just want total pressure, so I want to use the total amount of moles that are present. So the total amount of moles or pressure that's in this container is P times 10 liters, that's V. N total, I think, can I do this in my brain, is 2.3 moles of gas. That's the total moles of gas in this container, times our gas law constant, 0.08206. I'm not going to write the unit, I'm lazy. And then temperature is 298 Kelvin. All right, so now that I have PivNerd all filled out with the total number of moles of gas, I can see that the total pressure of this container is something like 5.62 atmospheres. All right. So let's actually go ahead and calculate what the mole fraction is of argon. So if I wanted to calculate the mole fraction of argon gas present in this container, just think about what is in your container. You have 0.1 moles of nitrogen, 0.2 moles of hydrogen, 2 moles of argon. And so to get mole fraction, you just take the mole amount of argon that you have present of that, substance that you're focusing on, and you want to divide by the total moles of stuff that's there, right? So you can calculate mole fraction for any one of these gases, but I just want to do argon so we can see that it is present in the largest quantity. So mole fraction of argon would be 2 moles of that argon gas is present over the 2.3 moles of gas that I have total. And you see something like argon is present in 87% of that sample, right? So that means the partial pressure that argon is exerting is 87% of that total, it's contributing 87% of that total pressure. So mole amounts, you can think about them individually or as the total sample to get that total pressure there. Okay, there's a lot of stuff. Okay, I'm just gonna keep going through because it seems like everyone wants everything. Okay, so, all right, so let's do this one. Which of the following gases has a density of that at this temperature and pressure? All right, so calculating density or understanding density of gases is a learning objective in chapter 10. And so my best strategy for calculating or thinking about densities of gases is to let the units guide you. So I'm asking you which one has this density. I can't just look at these gases and know which one has a density of 2 grams per liter. So I'm just going to go ahead and calculate all of them, all right, and see which one matches the 2 grams per liter that I'm going for. So density of anything is mass of your sample divided by the volume of your sample. So when working with density of gases, sometimes it's tricky to think where to get started, right? So the best way to get started, because I need a mass and I need a volume, but I don't know how much sample I have. So I'm going to use the easiest number I can think of, and that is 1 mole. Let's just pretend we have 1 mole of gas, right? So if I have a mole of gas, let's say I have a mole of helium gas, do I know how much it weighs? Yes. Where does that come from? Periodic table. Yeah. If I have a mole of gas at this temperature and pressure, do I know its volume? Yeah, I can figure it out. So mass here, as long as I have an amount to start with, and I'm going to start with an easy number, it's going to be 1 mole. Because if I start with a mole of gas, I know that the mass of that sample comes from the molar mass of that gas, and volume comes from PV equals nRT. But what is N in PV equals nRT? 1, because we made the assumption, let's start with 1 mole of gas. A lot of students, they struggle with that, and they're like, wait, why 1? And the reason is because we need to pick a number to start with, and 1 is an easy number. So I can figure out the volume of this sample because I know the pressure. That was, yes, I was given pressure in the question. N is 1, R is a constant, and I know temperature. So I can just calculate how much volume does 1 mole of gas occupy at these conditions. And so if you calculate that, so put in those temperature, pressure information, 1 mole times R, I'm not going to write it out, 303 Kelvin over 1.31 atmospheres. We see that 1 mole of gas at these conditions occupies like 18.9 liters. So that is my denominator in this density calculation. So there's 3 different gases here. So I need to calculate the density of each of them, right? So mass over volume for all 3. Do I have to do this volume calculation 3 different times? No, because we're just going to assume we have 1 mole for all of them. So for all of these gases, helium, argon, and xenon, when we do density equals mass over volume, volume's the same. The denominator's the same for each one of these calculations. Is the mass the same for all of these different substances? No, they have different molar masses. The only thing that changes here is whatever number is in the numerator. So we can go ahead and calculate these rather quickly. For helium, the mass is, what's helium? It's like 4, basically 4 grams. Again, remember, we're working with 1 mole of gas. So 1 mole of helium is 4 grams over that 18.9 liters. Argon is basically 40 grams over 18.9 liters. And then xenon is 131.3 grams over 18.9 liters. All of these gases, as long as we have 1 mole of stuff, will occupy the same volume. The only thing that changes is the mass. And then I think I can do this rather quickly. I believe argon would be the closest to 2.1 grams per liter. All right. All right. Okay, great. Any questions about that? So that's with densities. Densities, a lot of the trick is getting started. Just make the assumption, let's start with 1 mole of gas. Okay, so the packet I'm working on is the same place you got the Zoom link. It's on that page. All right, okay. So let's use our favorite equation again, PivNert. So I asked N. Yes, N stands for moles. We used moles previously in previous chapters using molar mass, stoichiometry, all of that. And so we can utilize PV equals nRT in stoichiometry again. We have this new way to play around with moles. So in this question, oxygen gas can be generated by the decomposition of potassium chlorate given by this reaction. If we have 2 liters of oxygen at this temperature and pressure, how many grams of reactant did we need to react? So the idea is we're just kind of working with stoichiometry, but just getting to moles a little bit differently. Back in chapters 3 and 4, we see these coefficients and understand that, oh, the coefficients mean that 2 moles of this reactant or potassium ClO3 is required to produce 3 moles of oxygen gas. Previously, we used like molar masses to get mole amounts, but now we can just use PivNert to get mole amounts instead, where I give you the volume, I give you the temperature, I give you the pressure, And so I have all the information I need to get the N amount to then use stoichiometry. All right, so given this pressure, volume, temperature data, I can calculate how many moles of gas I produced, then use stoichiometry, that's just chapter 3 stuff, to get a gram amount of potassium chlorate that I need. So if you put in these PVT information, I'm just going to skip that step. All right, you get that the moles of oxygen gas that you created was something like 0.0812 moles of oxygen, right? So now that I'm in the unit of moles of oxygen, I can now go ahead and use stoichiometry and say, oh, I can use that 3:2 ratio. And so stoichiometry says 3 moles of oxygen goes on the bottom because I want oxygen to cancel. 2 moles of potassium chlorate goes up top. I want a gram amount. So what do I need to get a gram amount? Molar mass, yeah. So I'll just do the work for you. Molar mass of this compound is 122.55 grams per mole, right? And so where does the 122 go in the next fraction, on the top or the bottom? The top, yes, because 1 mole goes on the bottom, 122.55 grams goes up top, right? So really, everything in red you've done a million times before in chapters 3 and 4. The only new part is I can give you pressure volume data to get N instead. And of course, N will only be used, or PIVNER will only be used when our product or reactant, whatever we're working with, is a gas. Like, could we PIVNER KCl here? No, we couldn't. So it would make more sense to do like gram data to get from like reactants to products. But when we're working with a gas, it makes more sense to use PIVNER because it's a gas. All right, so there we go. And then the answer you can find. Okay. All right, thank you for clarifying that. Okay, so that's the mathy stuff. Let's move on to something more conceptual here. All right. So let's think about, our intuition a little bit. When you heat samples up, if you think about like a cold gas sample versus a hot gas sample, we increase temperature, particles are moving faster because you're providing that sample with more kinetic energy. So there's a couple of equations we use to kind of predict properties of gases. One of those is root mean squared speed. I forget what the symbol for that is. I'm just going to say it's V. Or is it mu? I'm not sure. But regardless, root mean square speed is equal to the square root of 3 RT over molar mass of your gas. So if we look at this equation, we see that the root mean square speed of a gas sample is related and proportional to its temperature. Because you note, if we increase temperature in this equation, this speed increases. But if we increase the molar mass of our sample, if our sample becomes heavier at the same temperature, we actually see root mean squared decreases. So hot samples move faster than cold samples. Heavy particles move slower than light particles. And we can get those relationships just from this equation alone. So let's answer these questions. Which gas sample has the faster root mean square speed at room temperature, argon or neon? What are we looking for? We're looking for the lighter molecule. And so in that case, I'll give you molar masses. Argon's like 40 grams per mole and neon is like 20 grams per mole, right? So that means neon is going to be overall, those particles are going to be overall faster because they're lighter. Because if they're both at room temperature, they actually both have the same average kinetic energy present. But because neon is composed of lighter particles, they're moving faster. All right, so at which temperature will a sample of oxygen gas, so same substance, possess the faster root mean square speed? Cold or hot? Hot, yes. All right, and again, both of these questions just came from the equation itself. All right, which gas has a faster effusion rate? So effusion rate relates to collisions. A lot of the properties we look at relate to collisions. The more a gas collides with the sides of the container, the more a gas collides with each other, all comes down to kind of the properties of root mean square speed. So if a gas effuses, will it effuse faster if there's more collisions or less collisions? Less collisions? More collisions, yeah. So if a gas is colliding with the walls of the container more, we see that the gas escapes from a pinhole faster. I don't know if you've ever noticed, I mentioned this in my class, but I have a big captive audience here. You ever like go to a party and there's like helium balloons, right? If you're ever part of like the party cleanup, you go the day after. And if there's a mixture of like helium balloons and then like regular balloons that like people blew up with like their lung air, you'll notice that the helium balloons, they actually shrink faster, right? You go in the next day, clean up the next day, you'll see those helium balloons, they shrink down a lot faster than balloons that we just like blow up with our lungs. Because we exhale mostly nitrogen gas, CO2, oxygen, but helium is a lot smaller than all of those particles. So we see helium balloons, they shrink down a lot faster than just like regular balloons. And that's because helium's a lot slower, or a lot faster, because it's a lot lighter, and so therefore it effuses faster. So which gas has the faster effusion rate? It's going to be neon, because it's faster, more collisions, faster, more collisions, faster effusion. Okay, which gas possesses the greater density at STP? So does that mean I need to calculate it? No, we don't actually have to calculate it, because remember, density equals mass over volume. Remember the strategy? We start with 1 mole of stuff. And so for both of these, won't the denominator be the same number? So what will be different for both of them? Just the top number. So what substance are we actually, or what property are we actually comparing here? Molar mass, yeah, because we're just, we understand that the volume, the denominator is the same number. I don't actually have to calculate it, but I'm comparing the mass amount of that 1 mole of gas. So in this case, argon, if you have a balloon of argon gas versus neon gas at STP, the argon gas balloon is going to be heavier. Okay, which gas is going to deviate more from ideal behavior at high pressures? What do we think? All right, so if we're deviating from ideal behavior, can we use Pivnert? Now, we got to use the other equation. So the other gas equation we looked at was the van der Waals equation. So P plus some stuff, we have this A term. What does A stand for? Attractions, yes. And then we have this V term. A B term that's connected to volume equals nRT. So it's not a learning objective to actually do a calculation using the van der Waals equation. Instead, it's more conceptual. Do we understand what this A term is and what this B term is? A, you told me, is for attractions, while B is related to what? Size, yes. So at high pressures, the particles, there's going to be a ton of particles in a small space. That's how we get a high pressure. So at high pressures, the size of the particles start to matter. And so this question, how we approach it, which gas is going to deviate more at ideal behaviors, we are looking for the substance that the particles of that actual gas is significant. So really, we're just looking for the larger gas particle here. So if we think about, if I had a mole of argon and I condensed it down, how much volume would that occupy? If I had a mole of neon and I condensed it down, how much space would that occupy? So in this case, argon is going to deviate more because it's just a bigger atom. It's heavier. It has more electrons. It's going to take up more space. More electrons, more protons. It has more everything than neon. It takes up more space. Right? So high pressures, I want you to recognize that it's talking about the B term, the size term. All right. Okay, which gas will possess the larger A term for the van der Waals equation? So A stands for attractions. So of these two samples, which one are the particles? So if I have a sample of nitrogen, am I just going to have one nitrogen atom? No, you're gonna have like a billion of them. So if we look at nitrogen, and this is kind of a preview to chapter 11 and intermolecular forces versus CO, carbon monoxide, in which sample will the particles actually interact with one another? Is there actually some type of attraction? So in nitrogen gas, what kind of IMFs are present in nitrogen gas? London dispersion. Is that a strong IMF or a weak one? Very weak. What about CO? Does CO have LDF? Yes, but what's the detail here? CO also has dipole-dipole. So in which one are the particles more attracted to one another? CO, yes, yes. So some of you might think, oh, but the slide said that as B increases, A increases. What do you think the B term is for both of these gases? Calculate the molar mass of both of them. They have the same exact weight. So can we differentiate based upon the B term? No. So we actually have to look at the intermolecular forces of these two, and I try to make it obvious. One's polar, one's nonpolar, and so we can see all of that. Okay, so there we go. Why does argon have a greater density? Because it's heavier. The mass term, it has a higher molar mass per mole. Okay, so cool, perfect. That's a great segue into chapter 11, IMFs and liquids. Because the intermolecular forces between particles, between molecules, give us a lot of the properties that we see. So let's just review IMFs, right? As the total intermolecular forces of your sample increase, what do we observe? Boiling point temperature, how does that change? As the particles are more attracted to one another, increases because it gets harder to separate them. What are the other properties? Viscosity increases. Yeah, the particles, they're hugging each other more in the liquid phase. So if you're trying to pour that liquid out of a container, they're going to move slower because they're hugging each other tighter. What's next? Surface tension. It increases. Yes. What else is there? Vapor pressure. That's a tricky one. Yes, that's the one that decreases. And so since, again, I have a captive audience here, vapor pressure, a lot of students, they don't understand what vapor pressure is. They're like, it's a liquid. How is there a gas also there? All right. And so I ask my students to imagine nail polish remover. Can you imagine you have a cup of nail polish remover in front of you? Yeah. What phase is nail polish remover? A liquid. But you have that nail polish remover in front of you. Does it smell like anything? Yeah, but you just told me that that nail polish remover, which is acetone, it's the chemical acetone, you smell it, but it's a liquid in front of you. So how is that smell going into your nose? It's because acetone exerts a vapor pressure. Some of those acetone particles are in the gas phase and going up your nose, right? So when a sample exerts a high vapor pressure, that means there's a lot of gas particles of that same molecule above the liquid. Or I like to think, I tell my students that it means that the sample is smelly, right? The liquid sample is smelly. And so acetone has fairly low intermolecular forces. The particles are not very attracted to one another, so they let their particle friends leave the liquid into the gas phase so you can smell it, enter your nose, right? Okay. So that's the idea. So vapor pressure decreases. Okay. And I think the last one, it's like delta H of vaporization, energy to vaporize something also increases. Okay. Because most of chapter 11 is, you know, I can ask a question like which of these two things has the higher vapor pressure? It all comes down to differences in IMFs. Which one is the most viscous? It all comes down to IMFs. And so a lot of these things, again, just boil down to IMFs. Can you compare the IMFs in a sample? Okay, so let's look at these samples. And which one has the higher normal boiling point? All right, so if I'm asking for the higher boiling point, what am I actually looking for? Which sample has what kind of IMFs? The higher one, yes. Okay, so let's look at these two samples. We have a bunch of carbons in a row, and then a nitrogen, and then two nitrogens and a bunch of carbons. So a lot of the time it's us recognizing what is the strongest IMF that these two things share and looking for the difference. So I recognize here that like a bunch of carbons, that's London dispersion forces. This nitrogen kind of disrupts that and makes it a polar compound. Same thing with this compound. There's nitrogens there, so it makes it a polar compound. It's not LDF. It's not dipole-dipole that's going to differentiate these boiling points. What is going to differentiate it? Hydrogen bonding, yeah. But both of them have hydrogen bonding, right? NH groups, because there is a lone pair on that nitrogen. Both of them can hydrogen bond. So shouldn't they both have the same boiling point temperature? Nope. So the first one, the first compound can only hydrogen bond in one place. The other one can hydrogen bond in two places. So this one is going to have the higher boiling point temperature. Okay, all right, Br2 and ICl. What's the IMF that's gonna differentiate these two? Do both of them have LDF? Yes, but that's not gonna help us. What does help us? ICl is polar. Yeah, this is a polar compound. So this compound can have dipole-dipole. It's like little magnets. All right, so that one is going to have the higher boiling point temperature. All right, if you go ahead and like calculate you might want to like calculate the molar masses and compare molar masses to compare LDFs, but you'll calculate, oh, they're kind of similar, they're similar values. So that's not going to help us. But what is going to help us is one's polar while the other one isn't. Okay, I know that ICl is polar because you have two elements bonded to one another that are different. I don't need to know what the electronegativity difference is for both of them. I just know that they're different. Versus Br2 has, it's completely non-polar. The delta EM is 0 there. Okay. PH3 and ASH3. So maybe drawing the two compounds would be useful. So I recognize phosphorus and arsenic, they're both in group 5. Same thing as nitrogen, and I know like that NH3, the Lewis structure of NH3, I know that it looks like this, where there's a lone pair on nitrogen and two hydrogens attached to nitrogen. PH3 and ASH3 are actually going to look the exact same because phosphorus and arsenic have the same number of valence electrons. So you'll go through the same 6 steps for Lewis structures there. So that's the phosphorus compound, and then here is the arsenic compound. All right, both of them are in group 5. So they both look like that. So do both of them have LDF? Yes. Do both of them have dipole-dipole? Yes. Oh, so that's not useful. Can both of them hydrogen bond? No, neither of them can. So they both have LDF, they both are polar. So what I want to look here is see that, oh, one of them's a lot heavier, and that would be our arsenic compound. Since both of them have the exact same electron or molecular geometry, both of them are polar, I'm gonna step down to comparing LDFs here, and I recognize arsenic's a lot heavier. Like a lot heavier. Yeah, it's over double the weight of phosphorus. So that one is going to be have the higher boiling point temperature. Okay. All right, Br2 and xenon. What's the most important IMF in both of these? London dispersion, yeah. Are either of them polar? Nope, they're not. So LDF is going to be the thing that distinguishes them. So bromine, diatomic bromine, has a molar mass of about 160, and xenon is like 130. So which one has the higher boiling point temperature? What do you think? It seems like it's bromine, right? Because bromine's heavier. But is molar mass the only thing that distinguishes London dispersion? It's actually molar mass and surface area. So what has more surface area? A complete spherical atom like xenon, or bromine, which is 2 atoms bonded together? Bromine actually has more surface area. So that means the electrons on one bromine molecule can interact with another bromine molecule to make those temporary dipoles that London dispersion is. So bromine is actually the one that has the higher boiling point temperature. Also, let's think about this. At room temperature, bromine is a what? It's a liquid, yes. So does that mean its boiling point temperature, is it above room temperature or is it below room temperature? It's above room temperature. What is xenon at room temperature? Dr. N, I don't interact with xenon, but xenon is part of what part of the periodic table? Noble gases. So if xenon is a gas at room temperature, its boiling point temperature is what? Above or below room temperature? Below. And so this agrees, the idea that it's not molar mass that's making the distinction here, it's surface area. Comparing to the boiling points that we can get from just thinking about what these substances adopt at room temperature. Okay, all right. So for each of these pairs of substances, which substance exerts the higher vapor pressure? So really, what is this question asking? Which one has lower IMF? So it's literally the exact same question as we've been doing before, all right? We're still comparing IMFs. So CCl4, CBr4. So we're looking for lower IMF. So this time it's going to be the lighter molar mass things because LDF is the important factor here. Both of these compounds are nonpolar, but chlorine is lighter than bromine. All right. B, which one has the higher vapor pressure? This carbon chain or a carbon chain with a chlorine tacked on at the end? Just the carbon chain, because this is a non-polar compound versus this compound is polar. All right. Because there's that chlorine there. That chlorine disrupts the symmetry. Okay. All the all the shapes. Are all the shapes with lone pairs of electrons on polar except square planar? I'll ask you to review chapter 9 stuff for that. I'll have to go through all of them. I don't like coming up with absolutes. I like just drawing them. All right, last one, H2O and H2S. Which one has what are we doing? Higher vapor pressure, so lower IMFs. Okay, so both of these compounds, they have LDF. They're both polar because they're both bent. But can both of them hydrogen bond? But H2S has hydrogens. But are these hydrogens electropositive? No. So for hydrogen bonding, we're looking for 3 different scenarios. It's a hydrogen attached to either a nitrogen, a hydrogen attached to an oxygen, or a hydrogen attached to a fluorine. But that one's not going to come up very much in compounds. So you're looking for hydrogens attached to nitrogens or oxygens only. So yes, there's a hydrogen here, but it can't be any hydrogen. It has to be one of these 3. And so H2S cannot hydrogen bond. So this compound has the lower IMFs. It's going to have the higher vapor pressure. Water has extremely high intermolecular forces for such a light compound because it has 2 places it can hydrogen bond. Okay. All right. This one, which substance exerts the highest vapor pressure at their respective normal boiling points? When does a sample boil? Does water always boil at 100 degrees Celsius? Maybe. No. Yeah, what we learned is no, it doesn't. Water boils at different temperatures based upon what external pressure is on it. We learned on Earth, most of the time we recognize water boils at 100 degrees Celsius. But in Denver, they have to have a different set of cooking instructions. They have to cook stuff longer because water boils at a lower temperature there. So why do you have to cook stuff longer in Denver? Because water boils at a lower temperature. That it's actually easier to boil water in Denver because the atmospheric pressure is lower. So anything will boil when their vapor pressure equals external pressure. But on Earth, What is usually the external pressure of stuff on stuff? 1 atmosphere. That's what we call normal. So that means the normal boiling point of water, which is 100 degrees Celsius, is when the vapor pressure equals 1 atmosphere for water. That's what normal means to us. But in Denver, it's abnormal. When we boil water in a pressure cooker, that's abnormal because we're adding extra pressure to it. So can we answer this question? Which substance exerts the highest vapor pressure at its normal boiling point? Actually, all of them exert the same because all 3 of these substances will boil at once their vapor pressure is equal 760 torr on Earth. And because I said normal, normal means on Earth. So that means 1 atmosphere. So all of these have vapor pressures of 1 atmosphere when it boils. All right. I showed the demo in my class. I don't know about your class, but we took a vacuum pump. We put a cup of water inside the vacuum pump chamber. We pumped down the atmosphere inside that chamber. And yeah, I got water to boil because I reduced the pressure inside that bell jar. I was able to get that water sample to boil by reducing the pressure. And what I didn't do was heat up that sample at all. So once I lifted, the covering on it, and I grabbed that water sample after it was like rolling, boiling for like a couple minutes, it was kind of scary because sometimes we oftentimes have a bias. We think something that's boiling is hot, but we saw that, oh no, that water was still ice cold, but it was boiling, but for other reasons, not because we heated it, but because we reduced the pressure. Okay, is it still hydrogen if the electronegative atom doesn't have a lone pair? No, all of these electronegative atoms must have a lone pair. Where the interaction between hydrogen has to be with something that's electronegative. So all of these hydrogens are electropositive. So what the actual hydrogen bond is, I actually never drew a hydrogen bond. None of these 3 things that I have drawn here is a hydrogen bond. None of these. Because what is this? Is this a hydrogen bond right here? No, that's a covalent bond. That's a covalent bond. That's a covalent bond. What a hydrogen bond is when another HF molecule comes about, all right, and does this interaction. This is a hydrogen bond because this hydrogen is electronegative, and then the other fluorine molecule is hydrogen is electropositive, and then this fluorine atom is electronegative. This is a hydrogen bond. But what I'm trying to show you is when I just show you a single molecule, we think if I duplicated this molecule 1,000,000 times, like in a sample, is that sample capable of hydrogen bonding? So this bond, that is not a hydrogen bond. That's a covalent bond. We already learned about those in chapter 8 or 9. The new thing is molecules interacting with other molecules. So all substances exert the same pressure at their normal boiling point. Normal means external pressure of 760. So the size of the molecule won't matter for vapor pressure when it's all one. No, not necessarily, because how this question is worded. This question is worded, note how 9 is worded differently than 8. Question 8, I say, which one has the highest vapor pressure at the same temperature? They're all at the same temperature. Right? So here, IMFs matter. In number 9, I'm saying all of these samples are boiling at their respective boiling point temperatures. I didn't tell you what temperatures they are. If we wanted to get what temperatures the boiling points of these things are, yes, we would inspect IMFs. But just understanding when a sample boils has to do when its vapor pressure equals external pressure. All right. So yeah, 8 and 9, they're worded differently. So yes, water has a different boiling point than ethanol. They're different temperatures because there's different IMFs, but that's not what this question is asking. It's, do you understand what normal boiling point means? Yes, okay, all right. Okay, all right, last ones here. Okay, which statement is false about viscosity? So what's the trend with viscosity? As IMF increases, viscosity increases, yes. So if you work on cars or trucks and you talk about weights of oils, SAE ratings, as the number increases of those SAE stands for Society of Automotive Engineers. As that number increases, viscosity increases of different weights of oils, like hydraulic fluid is very They say heavy, but really they mean viscous. Okay, viscosity increases as temperature decreases. True or false? So we think about viscosity, it's how slow liquid samples move. So let's think about, let's make some pancakes. Okay, you take some maple syrup out of the fridge, all right? And you try to pour that maple syrup right out of the fridge onto your pancakes. How does it pour? Very slowly, right? What if I stick it in the microwave for 30 seconds and bring it back out? What happens? It flows faster. So what happened to viscosity when I put it in the microwave? It went down. So is this true or false? Viscosity increases. So viscosity is slowness of like pouring, all right? So if I cool it down, it flows slower. Is that true? Yes, okay, great. Viscosity increases as molecular weight increases. Yes, that's true, because as molecular weight increases, LDF increases, okay? LDF increases, your total IMF increases, so viscosity increases. Viscosity increases as intermolecular forces decrease. No, that one's false. Yeah, so that is the false one. But let's just go through all of them. Viscosity is resistance to flow. That's true. Highly viscous substance flows slowly. That's true. I just came up with other options. Okay. All right. Let's look at this phase diagram and estimate what is the normal boiling point temperature for this substance. Ooh, we get another chance with what normal boiling point means. Okay, so this is unlabeled, but most phase diagrams all look the same. This is how I like to think of it. So here, temperature, okay? Temperature, at low temperatures, you typically have what phase of matter? Really low, solids. At really high temperatures, you have gases. So this is a gas, this space. This one is a solid. And then this last piece, that is our liquid, right? So note how temperature is on this x-axis. Okay, what does normal mean in terms of boiling point temperature? It means on Earth, it means one what? Atmosphere. So what we want to do here is think about the phase changes that occur at 1 atmosphere. So if we set the pressure equal to 1 atmosphere, right here. So this horizontal line, these are your normal boiling and freezing points for this substance. So here's a point, but we need to make sure that we choose the right one. What are we looking for? Boiling point temperature. So do we want this first dot or this second dot? The second one, because we want the transition between liquid to gas. So we want whatever temperature this is. I don't know, that's like 175-ish, 175, is that an answer? Whatever, yeah, 170, sure. Okay. Let me ask you another question. Does this substance sublime on Earth? What does sublime mean? Solid to gas. On Earth, normal means 1 atmosphere. So is there a solid to gas transition along 1 atmosphere? But you might be looking at this graph and thinking, oh, but solid to gas transition, that's right here, right? That's right here. But you can only get this sample to sublime when you're at these reduced pressures. On Earth, you're not at these reduced pressures, you're at 1 atm. You are stuck right here. You're stuck right there if you're on Earth, unless you have access to big boy vacuum pumps or something, then you can go elsewhere. But yeah, on Earth, we're stuck on this 1 atmosphere line, all right? So this sample does not sublime on Earth. Okay, there we go. Okay, yeah, so let's just finish chapter 12 stuff, and then we can go to old stuff for the last hour. Okay, arrange the following substances in order of increasing melting point. Melting point, right? So this is solids, this is chapter 12, all right? So there's a bunch of different substances here, all right? So let's just go through, we talked about a lot of different bondings of compounds. So let's look at these things and decide what kind of compound they are. So think like, how would you name it? How would you, describe the bonding in these compounds? What is strontium oxide? What kind of compound is that? If this was chapter 2 and I asked you to name it, what kind of naming rules did I use? Ionic, yes. So we have something that's ionic. What about lithium fluoride? Also ionic, okay. What about CH4? What is that? Is that ionic? No, it's what? Molecular. If you draw a Lewis structure of it, it's a molecule, it's a molecular compound. Lithium bromide. Ionic. And this CH3OH, what is that? Molecular, yes, that's methanol, molecular. Okay, great. Wait, there's a mixture of things here. We got ionic stuff, we got molecules. So how can we determine melting points? So we talked about solids. We talked about 4 different kinds of solids. What is it? Metallic, ionic, covalent network, molecular, right? Each of them have different properties, including melting points. So of those, which ones has the lowest melting point of those 4 solids? Molecular. So we can go ahead and say, oh, these 2 have the lowest melting points. Do you agree? And then the other ionic things have higher ones. Okay, so of the molecular things, which one is harder to melt? The one with the OH group. Yeah, why the one with the OH group? Hydrogen bonding. So CH4 is going to have the lowest melting point because it has the lowest amount of IMFs present. Then it's going to be CH3OH. And now we need to decide on the 3 ionic things. I know that those ones are the highest. So amongst those 3, how am I going to decide melting point temperature? It's something you already know. Lattice energy, yes, we're going to look at lattice energy instead. So lattice energy, what do we inspect first? The charges. So strontium oxide, +2, -2, and then the other 2 is +1, -1. Okay, so which one is the hardest to melt? Strontium oxide. All right, so it's the lithium ones I need to decide based upon what? Because their Q1, Q2 charges are the same. We go to size. So which one has the higher melting point? The smaller fluorine or the bigger bromine? The higher melting point. Remember, to melt an ionic substance, you are kind of like half ripping the ions apart. So is it harder to rip apart ions that are close together or far apart? Close together. So lithium, which one it has the higher melting point? Fluoride. So it's lithium fluoride is and then lithium bromide there. Right, because bromide is bigger. Right, so to get the ordering here for the last ionic ones, it's just lattice energy. That's review of chapter, I don't remember, 8, I guess. But kind of the extension here to make this chapter 12 is recognizing, oh, I have a mixture of molecular stuff and ionic stuff. So I got to separate those ones. I know that molecular compounds always have lower melting points because you're just breaking weak IMFs. And then amongst those, you can look at the IMFs. And then within ionic compounds, you can look further at lattice energy. Okay. Does it mean is the melting point? Madison. Yeah, 150 would be the melting point. Yeah. Yes, and so that's why that's an option for this last question, 150, because I want you to think, if you did not label this graph correctly, if you thought that melting, right, if you thought, oh, right, a boiling point was like between these 2, then you might pick the wrong temperature there. Okay, that was a tricky one. All right, so here are other ways we can ask about solids, and that's, remember, there's 4 types of solids, and based upon the properties, you can figure out what it is. Okay, we have a white soft solid, highly insulating, meaning does it conduct electricity or not? No. Okay. When the solid is added to pure water, it dissolves completely, and the resulting solution does not conduct electricity. What is it? What is it? Yes, it's a solid. What kind of solid? It is not ionic, because if you dissolve it in water and it does not conduct electricity, it means that there are no ions present. And so if there's no ions, it cannot be ionic. So this must be a molecular solid. Also think about it. I gave some distractors, but they're really bad distractors. So like a weak electrolyte, does that conduct electricity? Yeah, it conducts electricity, back from chapter 4. So it can't be that. Also, we didn't talk about weak electrolytes in our solids chapter. Ionic solids, they will be strong electrolytes in solution. Will metallic solids even dissolve in water? No. Yeah, of course we can identify it. Okay. Isn't the Q1, Q2 bigger for lithium bromide than lithium fluoride? No, it's not. I accidentally wrote a 2, but it should be a 1. Bromide is -1. They're both the same Q1, Q2 product. Yeah. Use your intuition. I make mistakes. Someone should have just said something. Okay. All right, last one. Order the following in increasing electrical conductivity. So let's think about this. We learned about metallic solids, network covalent solids. What's on this part of the periodic table? What's over here? What kind of elements are here? Non-metals. And then what's basically everything else? A metal. Okay. So most of the metals fall under metallic solids, all right? And then non-metals, they're their own class. They can be molecular solids, they can be covalent network. So metals, they conduct electricity. Non-metals don't. So that's kind of our thinking here. And then of course we have weird ones in the middle, are metalloids, and they will have behaviors between that of metals and non-metals. So if we look through these different substances, I recognize carbon is what kind of element? A non-metal. Lead is a metal. And then germanium is a semi-metal. So in terms of electrical conductivity, it's going to go carbon, germanium, lead. Lead is most metallic, carbon's the least metallic. All right, zinc, arsenic, bromine. Zinc is a metal. Arsenic's a semi. Bromine's a non. And that's how we approach that. So this is going to be bromine, arsenic, zinc. Metals conduct, non-metals don't. As much. Okay. All right, so that's it. So what chapter or midterm do we want to go over? Okay, if someone gives me a number, a question number, I will do it right now. Someone say it. 5? Wait, 5? Oh no, give me a question number. 40. Perfect, MO theory. I love MO theory. Okay. All right, so let's so this is question 40. It's on page 14. So this is the exact MO diagram. Sometimes I call it a spaghetti diagram because it looks like spaghetti. That you get on the exam. So, you know, there's a lot of information on this graph, but we have to understand, how do we break this graph down, or, you know, this diagram down? What does it mean? So what is being depicted on the sides here? What are these? What's those 3 lines? What is this 1 line? Those are orbitals, but what kind of orbitals? These are atomic orbitals. Atomic orbitals. So the orbitals of your atom. So if I'm combining 2 oxygen atoms, I put the atomic orbitals of 1 oxygen over here, and then the atomic orbitals of the other oxygen over here. So these lines are the s and the p orbitals for your atom, for your two atoms, right? Then what are the lines in the middle here? The molecular orbitals, because in order to, when we bring together two atoms, they're no longer atoms. Once you bring them together, now you have a molecule. So when you combine atomic orbitals, you get molecular orbitals. So if you combine two atomic orbitals, you get two molecular orbitals out. If I combine a total of 6 atomic orbitals, I get 6 molecular orbitals out. So what we see here is a total of actually 1, 2, 3, 4, 5, 6, 7, 8 atomic orbitals coming together. So without even counting, how many molecular orbitals are in the middle? That should say MO. 8, yes. Okay. So how do we label these lines? I like to start from the bottom and recognize if we combine 2 s orbitals, we're going to get a constructive orbital and then a destructive one. Okay. I don't know how to get rid of that. I'm sorry. So what is this, the label for this first one? Sigma. Then what comes next? Sigma star. All right. And then what is 3 and 4? Sigma again, and then pi star, and then sigma star. If we look at the other MO diagram, sometimes these two are swapped around. Okay, so note that all sigma MOs always come in a like there's a single line. See, single line, single line. But pi interactions always come in pairs. So pi interactions will always have 2 lines with them. So if you look at like one of the other graphs, it goes like 1, 2, 1, 2, something like this, right? So I know the orderings of these MOs. It's sigma, sigma star, then the next one is pi. I know that this is pi because pi's always come in pairs, yes, and then the next one is sigma, then pi star, then sigma star, right? Pi's always come in pairs. Okay, so that's the other one. So remember there's like 2 of these. There's 2 of these. But this one is just happens to be for oxygen, fluorine, and neon. Okay, so what orbital is the combination of 2 py orbitals oriented perpendicular to the internuclear axis of oxygen, which will produce the molecular orbitals in what places of this diagram? So if I have 2 oxygen atoms and we're combining them, right? That's the bond between oxygen. Perpendicular to the internuclear axis, does it mean that the interaction is this way, or is it this way? It's like this, yes. So the p orbitals are not interacting like that, right? That would be along the internuclear axis. What the interaction's actually happening is like this. And we know what kind of interaction is this. Pi, yes. So that's a pi interaction. So this interaction would produce which orbital? 4 and 5. You combine 2 atomic orbitals, you always get 2 MOs out. So you actually get a pi and a pi star. Because did I say anything about constructive or deconstructive? No. So it actually produces both. If I asked, you know, if I actually showed the interaction, if I said it was like this kind of interaction, it was like this or something, right, where the phasing all matches, then this would be constructive. This would just be the pi interactions, not the pi star, right? So I want you to recognize that it's the side-by-side interaction, orbitals oriented perpendicular to the internuclear axis. So that would be pi. Let me change the question actually, and let's answer it again, but I'm going to change the wording. The combination of 2 p orbitals oriented along. Which molecular orbitals, I'm going to just tell you that there's 2 of them, make this interaction. Which ones? Which 2 MOs? So it's along the internuclear axis. So Yes, it's a sigma, but remember, there's a bunch of sigmas on here. Which one is it? It's 3 and 6. But you might have a friend near you thinking, but I thought 1 and 2 were also sigma. Aren't those also sigma interactions? Yeah, but what's the problem? Those are sigma interactions between s orbitals. Well, how did I know it's not s? It's because I told you that they're p orbitals. Yeah, okay, great. All right, okay, rest of page 14. Okay, sure. Let's do the rest of page 14. I like specifics. If you just tell me chapter 5, that's not going to help me. Okay, so according to MO theory, when we remove an electron from nitrogen, the cation will what? So what's going to be helpful here is if we start with the MO diagram, which I don't have, so I will get the MO diagram. Let's see if I can't do this. Let's copy you. Copy. Ugh. Oh my gosh. Okay, whatever. Okay, so we are working with, what are we doing? Nitrogen, or diatomic nitrogen. So nitrogen, if you write out its electron configuration, it's 2s2, 2p, how many? 3? So each of the nitrogen atoms are contributing 5 electrons. So there's 1, 2, 3, 4, 5 electrons here. All right. These electrons do have spin, but I don't care about the spins. All right, I'm just drawing the electrons quickly. Right. So now we just want to rearrange those 5 electrons that were in atomic orbitals. Now we want to put them in MOs, following the same exact rules as before. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So that's the MO for diatomic nitrogen. We can calculate the bond order. We just have to remember the sigma, the bonding versus anti-bonding stuff. So we have sigma, sigma star, pi, sigma, pi star, sigma star. So I see that there are 3, or I guess 6 electrons in bonding orbitals, and no anti-bonding electrons. So we see that nitrogen has a bond order of 3, and that's exactly what the Lewis structure would predict as well. These 2 sets, they cancel each other out, so I'm not including those. All right, so normal nitrogen has a bond order of 3, where we take bonding electrons, subtract anti-bonding electrons, divide by 2. Bond order of 3. All right, bond order equals 3. So what does the question say? When we remove an electron, all right, so we take this MO and we remove an electron. What electron do we remove? Just the topmost, yeah. So we remove an electron, there is N2+. So if you're just cognizant of what kind of electron did I remove? What kind of electron? A bonding electron or an anti-bonding electron? Bonding. So removing a bonding electron weakens the bond, because now what is the bond order? 2.5. Because now there's only 5 bonding electrons over 2. That's 2.5. All right. So that should allow us to answer all these questions. The bond. So I've removed an electron. The bond order decreases. It goes from 3 to 2.5 because I removed an electron from a bonding orbital. The bond length changes how? It lengthens, yes, because the trend is as bond order increases, strength increases, but length decreases. Okay, bond enthalpy is now stronger, or no, it's weaker, because we went to 2.5. Yeah. Triple bonds stronger than double bonds, stronger than single bonds. And then finally, the cation is what? Diamagnetic or paramagnetic? Para. Diamagnetic means everything is spin paired. Okay. Paramagnetic means you have at least 1 electron that's unpaired. And so that would be this electron right here. I know I didn't draw the spins, but recognize that if there's 2 in them, they must be spin paired. Okay. Okay, should that only be 3 instead of 3 and 6? 4 electrons, oxygen each. Oh, that was the last question. Wait, not sure what that question is referring to. Okay. All right, so, all right. So let's just do one more. According to MO theory, when an electron is added to carbon to produce anion. So since this is diatomic carbon, can I use this diagram still? I think I can, yes. Yes. Yes, because this diagram works for diatomic carbon or boron, carbon, and nitrogen. So same thing. So let's start with carbon as the neutral atom. So carbon is 2s2, 2p2. So, but I have 2 carbon atoms. So each carbon atom is giving me 4 valence electrons. So there's a total of 8 valence electrons going into that MO diagram. I'm not going to bother with the atomic orbitals or atomic orbitals. So I'm just going to put the 8 in the center. 1, 2, 3, 4, 5, 6, 7, 8. So for neutral carbon, diatomic carbon, what is the bond order? 4? 2. It's 2. So let's just remember, so this is pi, sigma, sigma star, sigma. So the equation for bond order for MO diagrams, what is it? Bonding electrons minus antibonding over 2. So I can go ahead and count all of the bonding electrons. 1, 2, 3, 4, 5, 6. There's 6. And then there's a total of 2 antibonding electrons. So minus 2 over 2, this is equal to 4. Or no, it's not, it's equal to 2. It's 4 over 2, so it's 2. So this has a bond order of 2. But I use a trick here. I recognize it's bonding minus antibonding. So since this is entirely filled, it's going to be 2 minus 2. So I can just ignore those electrons and just look at the electrons that are up here, right? Once that this one is completely filled, right? So it's just a little trick. So neutral carbon has a bond order of 2. So what are we doing? We're adding an electron. Is that what we're doing? Yeah, so we add an electron, but what kind of orbital is it going into, that added electron? Can I just put it anywhere? No, it has to go into sigma. Yes, into the sigma. So we're adding an electron to a bonding orbital. What happens to the strength of that bond? It gets stronger. Bond order goes up to 2.5 if you just calculate it. So bond order increases. Bond length does what? Shortens, it gets stronger. Now it's paramagnetic, right? Because now you have that unpaired electron right there, right? So that's how we do that. Isn't N2 plus nitrogen with, okay, so I see the question. All right. So nitrogen has, diatomic nitrogen has a total of 10 electrons towards it. N2 plus, that entire molecule just has 1 electron removed from it, just like when we did like Lewis dot structures. When we were working with nitrogen versus nitrogen plus, that plus just says we remove 1 valence electron from the count. We don't remove a electron from each of the nitrogens, just 1 of them. So N2 plus would have 9 valence electrons present. Same thing with C2 minus would have 8 comes from there, and then an extra one, it would have 9, also have 9 valence electrons to it. Okay. Okay, so, all right. Someone else give me a number. Page 10, well, what number? Question 17. 17, okay. Chapter 1. Weren't those simpler times? Okay, 3 students conducted an experiment to determine the mass of a gold coin Here are the results. The instructor determined the true mass of the gold coin to be 63.6 grams. Okay, so this is a question on accuracy and precision. So accuracy, you're comparing the average, typically your measured average, like if you take a measurement and you take the average of all your data, you're comparing it to what? True value, yes. But when we measure precision, what are we looking at? We're just looking at the range of the data for each of those people, all right? We're seeing how close that your data sits next to one another. So if I go ahead and calculate the average, look at the range of the data for the 3 trials for these three students. Okay, I don't feel like doing the math, so I won't. Okay, so averages are 63.1, 63.4, 64.2. Ranges 1.6, 0.7, 0.1. So which student is the most accurate? We're looking for the average that is closest to the true value. What is the true value? 63.6 grams, yes, because I told you the true value, all right? What if I didn't tell you the true value? You can't figure it out, yeah, all right? But could you still do precision? Yes, because precision here, who's the most precise? Student C, but since I did give you the data, student B is the most accurate, okay? But again, the answer would be could not be determined if I didn't give you the second sentence, all right? Okay. I personally want to do question 16. Okay, we have the volume of a room is this size. What mass of air, or here's the mass of air. What is the density of air in grams per milliliter? So density, we need a gram amount, we need a milliliter amount. That's our goal. I give you a volume. Here's my volume. Here's my mass. So my strategy here is let's turn that mass into a gram amount. That's simple enough. Kilograms to grams. But then what's the tricky one? Turning meters cubed to a milliliter. Yeah, that's the tricky one. So let's do that one second. Let's do the first one. All right. The denominator in this density is going to be 44.8 kilograms. 1 kilogram is 1,000 grams. Is that something you need to memorize? Yes. And so there is 44.8 times 10 to the 3 grams of air in this room. So that's your numerator. Now the hard part is getting the denominator. So we have 38.0 meters cubed. But I need to get that into a milliliter. So there's another conversion that you need to memorize that's going to be helpful here. And that is 1 centimeter cubed equals 1 milliliter. All right? Because that's the conversion that gets us from the cubic volume realm to like the liquid volume realm. Very useful. All right? So this is more useful to us because I can actually relate a meter cubed to a centimeter cubed. All right? But should you spend valuable space in your brain to memorize how many cubic centimeters are in a cubic meter? No. But what should you memorize? That 1 meter equals 1 centimeter? 100 centimeters. Yeah, 100 centimeters. Oh, 100 centimeters. Centi means century, means 100. Yeah. So how does that help us? I just need to cube it. So 1 meter cubed, 1 meter cubed, oh, stupid pen, is actually equal to 100 cubed centimeters cubed. All right, so that's the conversion. And so to do that, putting that all together, 1 meter is 100 centimeters. All right, just cube that whole thing. And then you can do the 1 centimeter cubed is 1 milliliter. And so what I would put in my calculator is 38 times 100 cubed times 1 or whatever, and then that's the answer that you would get. What does my calculator say? 3.8 times 10 to the 7 milliliters. So a lot of milliliters. So that's your denominator. Divide both of those things. And then you should get an answer, a density that has 3 sig figs. Because this number has 3 sig figs, the kilogram number, and then your volume also has 3 sig figs, right? But this has, how many sig figs does 1 meter equals 100 centimeters have? Does it looks like it has 1 sig fig, but does it? No, it has infinite. Does that mean it has no sig figs? No, it means that you can just ignore it. Infinity is always bigger than any number. So that means we're looking for things with finite number of sig figs. This has 3, that has 3, so it's probably best to do 3. Okay, all right, I wanted to do that one. Okay, so let's do 20, okay, 23, I guess? 23. No, I want to do 20, and then we'll make our way to 23. Okay. Caffeine has this chemical formula. How much does 0.38 moles of caffeine weigh in grams? So how do I go from moles to grams of a compound? What do I need to use? Molar mass, but I don't have the molar mass of caffeine. That's not a value on the periodic table. So how do I get the molar mass? Periodic table. And so, but how do I do it? You got to add them up. So there's 8 carbons, so 8 times 12.01. Add 10 times hydrogen, so 1.008. Add nitrogen, so there's 4 nitrogen, so 4 times, what is that, 14.00 or 01? 01. And then 2 oxygens, 2 times 16.00. You know, we give you, I remember the first week of class, do we get the periodic table? Of course you get the periodic table in exams. But I promised a lot of students, like you'll probably memorize a lot of the molar masses of elements. Like, do you know what carbons is? 12.01? Yeah. You just use it so much. Okay, and then you add all of those up, and you see that the molar mass of caffeine is 194.19. But what's the unit? What's the unit? Great. Is it just grams? It's grams per mole, because the meaning of this number is that if I have 1 mole of this compound, it weighs 194 grams. But do I have a mole of this compound? No, I only have 0.38. So I can set up dimensional analysis and say, okay, for every 1 mole, I have 194.19 grams of sample, and then this sample weighs 74 grams. Okay, that's the easy one. So let's do this one. How many atoms are present, nitrogen atoms are present in 250 grams of caffeine? All right, so this one's a little bit harder. We're going from the gram realm to the particle realm, but there's actually more steps here. So we have 150 grams of caffeine. I'm going to use that same molar mass, but this time I'm going to put 194 where? 194 grams is going to go on the bottom. Yes, I like your enthusiasm. 194 grams on the bottom, 1 mole up top. But this is moles of what? Moles of what? Caffeine. Is that the answer I want? No. I want to get to nitrogen atoms. So there's a couple ways you can do this. If I have 1 mole of caffeine, how many moles of nitrogen atoms do I have? 2? 4. How did you know that? The chemical formula, yeah. So whatever number this is that we just got right here, we need to multiply that number by 4. But dimensional analysis works too. 1 mole of caffeine is 4 moles of nitrogen. Am I done? No, we go one step further. I asked for individual atoms, so what do? Avogadro's number, 1 mole of anything, in this case it's nitrogen, atoms, 6.022 times 10 to the 23 nitrogen individual atoms, right? I used to teach Gen Chem, but I gave like paper exams. And I remember doing this exact same question on a review, but on the exam, instead of asking for nitrogen atoms, I asked for hydrogen atoms instead. So if I asked for hydrogen atoms, how would the work here change? You just use 10 instead of 4. But in my review, when I taught that class, the example we did in class was of nitrogen, but on the exam I asked hydrogen. 50% of the class put 4. Put 4 down. They just put 4. I don't know, they just memorized the muscle memory of putting it all together, but they didn't actually look at the stuff. Yeah, okay. So there we go. Perfect, okay. So let's keep going. All right. What is the empirical formula of the compound that is 81% fluorine and 19% carbon by mass? Yeah, so how do we get started? Assume, I want to make an assumption. What should I assume? If I have 100 grams of sample, because if I have 100 grams of sample, that means I have 81 grams of fluorine and 19 grams of carbon. And I want to do that because my goal here is to get a mole ratio. I can't turn percents into moles, but I can turn grams into moles. And so I'm going to do that. Grams to moles, use the respective molar masses. Fluorine is 19 grams, 1 mole of fluorine. And then carbon's 12.01, but you've memorized that by now, is 1 mole of carbon. And so you do that and you get a mole amount. Okay, and so if you calculate that, my compound has my 100 gram sample has 4.26 moles of fluorine and then 1.58 moles of carbon. So does that mean my mole ratio is 4 to 2? Should I just round these numbers? No, what do I do? Divide by the smallest one. So that in that case, it's the 1.58. And what this does, when I divide by 1.58, it ensures that the mole ratio for carbon is 1. So for every 1 mole of carbon, I have 2.696 moles of fluorine. So now I round, what, right? It's a 1 to 3 ratio, 1 carbon, 3 fluorines. No, you don't round. What do you do? I'm going to multiply by some factor to make this fraction a whole number. And sometimes it's just guess and check. All right, so like take this number, multiply by 2. Take that number, multiply it by 3, by 4, by 5, until you get a whole number. And so I think for our case, if you multiply by 3, because this is really close to 0.66, like exactly 2/3, you see that you get a whole number. So this is basically for every 8 fluorines, there are 3 carbon atoms. And so the empirical formula is C3F8. All right, so a couple things here. Percentages, turn those into gram amounts. You need a gram amount to get to mole amounts. Divide by the lowest number, and then you get your mole ratio. Sometimes you do have to multiply by some type of integer to force that to be a whole number. Okay, cool. Okay. Let's do, yeah, 22. Okay. Was this one asked? Probably. Okay. Calculate the mass of the excess reactant remaining at the end of this reaction when 90 grams of SO2 reacts with 100 grams of O2. Okay, so this is the strategy. I give you amounts of the 2 reactants, and I need to figure out which one runs out first. One of them has to run out first. I can't look at these numbers and predict which one runs out first, so I just have to test both of them. So my strategy here is to convert these gram amounts into mole amounts, do stoichiometry twice. I'm going to do stoichiometry twice. I have to check. The idea here is I'm going to do grams to moles, to moles, to grams. Actually, I don't really have to go to grams at the end. I just need to see which one runs out first. And so to do that, I'm going to convert these gram amounts of reactants to either gram or mole amounts of my product. So if I have 90 grams of SO2 And I give you molar masses, how nice. 64.1 grams of that is 1 mole of stuff, SO2. But I want to go to the product. I just want to see how much product I make. So for every 2 moles of SO2, I make 2 moles of SO3. I'm not going to convert that product to grams. I don't have to. Why don't I have to? The question doesn't ask for it. So I'm not going to bother using the molar mass of SO3 to get a gram amount, right? So that mole amount, I make 1.4 moles of SO3. Oh, and I just looked at my key. I did the key a little bit differently, and that's fine. There's different ways you can do this, okay? So I'm gonna just do it this way, right? So what this means is that if all of the 90 grams of that reactant reacts, I will make 1.4 moles of product, right? But now let's do the same thing for O2. Let's pretend 100 grams of O2 reacts, and let's figure out how much product I make. So the same thing, but you want to use the appropriate molar masses. 32 grams is 1 mole of O2. Stoichiometry is a little bit different. 1 mole of O2 is 2 moles of that SO3 product. And so what you see here, dang it, since I did it different than my key, I don't have the numbers. 100 divided by 32 times 2. If 100 grams of oxygen reacts, I make 6 moles of my product. So based upon these numbers, which number matters? 1.4 or 6.2? Which number matters to me? 1.4. That's the actual amount of SO2 I make. This 6.25, that's assuming all of this O2 reacts, okay? But it's not going to, because I'm limited by the amount of SO2 that I have, the other reactant. So SO2 is my limiting reactant, right? And 1.4 moles of the product, this is my theoretical yield. All right, I could convert those into gram amounts, but I don't have to. All right, I know that the question didn't ask for this, but let's just be comprehensive, right? Okay, so what do we actually want? I want the mass of excess reactant remaining at the end of the reaction. So based upon the work that I have up here, which reactant is in excess? Oh, oxygen, yes, but how much of it? That's the question. So once we've figured out what the limiting reactant is, the limiting reactant dictates our theoretical yield. The limiting reactant also dictates how much oxygen I consume. So what I'm going to do is I'm going to do this same work again with SO2. I'm going to assume all of the SO2 reacts. But this time, instead of going to a product, I want to know how much O2 do I consume instead. All right, so I'm taking this green path. I'm going to do stoichiometry again. Yes, I did stoichiometry 3 times now, but that's okay. I'm going to take that 90 grams of SO2, but this time I'm going to go to O2. So I still need to use molar masses. Is 1 mole of SO2. And then now I want to go to O2. So I see stoichiometry says 2 moles of SO2 requires 1 mole of O2. Since this question is asking for a mass, a gram amount, now I will go to, I'll use the molar mass of O2. So 1 mole of O2 is 32 grams. And so this reaction, if all of that SO2 reacts, maybe 4.1 divided by 2 times 32, will consume 22.5 grams of O2. Is that my answer? No, my answer is actually going to be 100 minus that number, because that's how much is left over. So what's my answer? Is it E? Hopefully it's E. It's E. Okay, what if you chose the wrong limiting reactant and you did all of this? You'll get a negative number. And we should be able to recognize, oh, that can't happen. That means you picked the wrong limiting reactant. Okay. Could we also find the percent yield of this question? No, we can't, because we weren't given an actual yield, right? So we just have a theoretical yield. A percent yield, now that's a great question. A percent yield is actual over theoretical. So everything we just did on this page was theoretical. We assumed 100% of everything reacts. We did, we used the stoichiometry, like exactly what was shown on the balanced chemical equations. So everything we calculated here was theoretical. Actual is what you actually measure in lab. So since we weren't given that information, we can't actually get percent yield. But if I just said, added that little piece, then we could. Okay. All right, so 23, we made it. Okay. Which are weak electrolytes? Weak electrolytes. Select all that apply. So weak electrolytes, do they conduct electricity? Yes, but do they do so strongly? No. So let's just go through all the rules. Strong electrolytes, weak electrolytes, non-electrolytes. What are strong electrolytes? Strong acids and bases. What else? Anything that's ionic. Yeah, so NaCl, calcium chloride, strontium hydroxide. Yeah. Okay, weak electrolytes. Weak acids and bases. Yikes, do I have to memorize all of those? No. And then non-electrolytes, how do we identify those? Usually those are just molecular things. Anything that's not made up of ions. Okay, so how do we differentiate these strong acid bases and weak acids and bases? Do we have to memorize both? No. There's how many strong acids? 7. And how many of you are moving on to 1220? Okay, you need to memorize those 7 strong acids, because basically all of 1220 is we're looking at all of the weak bases and weak acids, all right? And so you need to be able to recognize what is a weak acid, and you can do that if you know the 7 strong, because you just are like, oh, it's not one of the 7 strong, it must be a weak acid. So there's 7 of them. And so how I memorize it is I look at the periodic table, and it's all of the halogens except fluorine. So for binary acids, so HCl, HBr, HI. So those are the 3 binary strong acids. Then there's nitric acid. Then there's sulfuric acid. And then there's the 2 chlorates. So chloric acid, so that's HClO3 and HClO4. Those are both strong acids. So those are the 7 strong. So that means if you have any other acid, so H attached to anything else, it's a weak acid. The most common weak acid that folks forget about is acetic acid, and the reason is the way we write it out. So acetic acid looks like this, CH3COOH. That is an acid. It's one of the acids where sometimes the H is tacked on the end, and the reason is because it looks more like the Lewis structure. Sometimes I'll write acetic acid this way, HCH3COO. Sometimes I'll write it that way so you can like clearly see it's an acid, but do recognize that acetic acid can be written differently. It's not always HC2H3O2. I feel like when I was in high school, that's how I remembered acetic acid, but this formula tells us very, very little about the structure. Chemists oftentimes want the formula to kind of represent the structure if we can. Okay, so let's go through these. Why don't we just say whether these are weak, strong, or non-electrolyte? So the first one, HCl, strong. Oh, right, it's right there. Yeah, so the second one, it's a weak, yes, that's acetic acid, very good. NH3, oh, that's the one I didn't say. So weak acids, we covered. Well, what about weak bases? In Chem 1210, there's only one that you need to know for now, and that is NH3, ammonia. NH3 is the only weak base you need to know. So NH3 is a weak base. So it's a weak electrolyte. In Chem 1220, you're going to learn all the other weak bases. Okay. Last one, KOH. KOH. Non-strong. Yes, it is a strong electrolyte. Why? It's a strong base. Also, it's ionic. So that idea kind of falls under both, okay? Because strong bases are also ionic compounds when we name them. Okay. Okay. Yes. All right. So everyone's asking for the BCA table. No, for 22, it's the same thing. It's the only difference is that the change, I recognize that this change is what dictates the change in the oxygen line. So that's basically the difference. Okay, 24, okay. Oh, actually, do you want to do 24? Is 24 okay? Okay, all right. Okay, consider the reaction here. If these things are mixed, how much silver chloride is produced? Okay, so I could technically do a BCA table here, but I don't want to. Because here's the thing, if a BCA table is just meant to organize your thoughts so you can choose the correct limiting reactant. That's the whole idea, is that if you completely fill out a BCA table, you'll get all positive numbers at the end. If you fill out a BCA table and pick the wrong limiting reactant, you're gonna get negative numbers at the end, and that doesn't make sense. So that's the big idea here. You don't have to do a BCA table, as long as you can think about it logically. So we're mixing two different reactants, and I'm asking you how much product you make. Do you see how this is no different from that SO2 reaction that I did? It's no different, but the only difference is instead of giving you gram amounts, I give you molarities. That's the only difference. And actually, this one's kind of easier because I'm telling you, you're mixing 1 liter of 1 molarity silver nitrate. So hopefully you can do this in your head. How many moles of silver nitrate do I have? 1 mole, okay, of silver nitrate. Okay, I'm mixing 1 liter of 1 molarity barium chloride. So how many moles of barium chloride do I have? 1 mole of barium chloride. So if you look at this balanced chemical reaction, you consume silver nitrate twice as fast as you consume barium chloride. Which one of these reactants is going to run out first? The silver nitrate's going to run out first. So silver nitrate is what? Limiting or in excess? Limiting, right? And so that means if silver nitrate is limiting, I'm going to consume all of that silver nitrate. So 1 mole of silver nitrate is going to get converted into that silver chloride. So I can use stoichiometry here. It's a 2-to-2 ratio or 1-to-1. So 2 moles of silver nitrate, 2 moles of silver chloride, that I will produce 1 mole of silver nitrate as well. Or sorry, not silver nitrate, sorry, silver chloride. All right. And then to get a gram amount, just use the molar mass. So you make 143.3 grams of it, right? Because I give you the molar mass, right? So I just logicked my way through that. I recognize, oh, silver nitrate's limiting. The limiting reactant always dictates how much product I make. So I can just do it that way. Or, yes, we can do a BCA table. So let's do a BCA table for this one because it's easier. So I'm gonna, let me just copy this. Let's do the BCA table, all right? BCA stands for before, change, and after. So before this reaction, I have 1 mole of silver nitrate, 1 mole of barium chloride, nothing of that. Which one's the limiting reactant based upon this data? Silver. And it's clear to see that because the numbers are easy. But let's, for fun, pretend that we chose the wrong one. Do you want to choose the wrong one? Let's pretend we think barium chloride runs out first. So if barium chloride runs out first, it means we consume all of it. So -1, so we have 0 at the end. The change line is always dictated by stoichiometry. So if I consume 1 mole of barium chloride, how many moles of silver nitrate must I also consume? 2. So it's -2. If I consume 1 mole of barium chloride, how much silver chloride do I make? +2. And then barium nitrate, +1. And so when you add them up, you see, oh, the after line is -1. You can't have that. And so in this case, when we do the BCA table deliberately wrong, we get negative values. And then what does that imply about this 2 moles of product that I made? Does it mean anything? No, it means nothing, all right? And that's the point of a BCA table, that it'll show you whether you're right or wrong. So this is completely wrong. So let's do it correctly, where we correctly assume that silver nitrate is the limiting reactant. Limiting reactants get fully consumed. So what is the change for silver nitrate? -1. So if I consume a mole of silver nitrate, how much barium chloride do I also consume? 0.5, yes, because it's a 2 to 1. So it's -0.5. How much silver chloride do I get? It's 2 to 2, so it's +1, and then this one is +0.5. Now let's add up everything and see what we get. There is 0.5 moles of barium chloride, 1 mole of silver chloride, 0.5 moles of barium nitrate. Do these numbers, do these matter? Yes, they do. Okay. And so the reason we do a BCA table is useful to us because we also can figure out what is the concentration of chloride after this reaction's complete. Okay, so I have like a minute. I'm gonna just still finish this problem. So what is the concentration of chloride after this reaction is complete? So the beauty of a BCA table is we already got everything. We know everything about our solution after this reaction is done. I have no silver nitrate left. I have half a mole of barium chloride in my container. I have a mole of silver chloride. It's a solid. It's sunk in at the bottom of the container. And I have half a mole of barium nitrate. It's all dissolved up in there. So if I want the concentration of chloride ion, I need to ask myself, what in this container, all of this is in my beaker, what contributes chloride ion to my solution? Does barium chloride give me chloride ion? Yes. Does silver chloride give me chloride ion? No. Why? But there's a chlorine in it. It's a solid sunken at the bottom, and then barium nitrate does not have any chloride. So all of the chloride is actually coming from barium chloride. If I have 0.5 moles of barium chloride in this solution, it's a strong electrolyte. How much chloride do I actually have? How much chloride is there? 1. Yeah, you have 1 mole of chloride, but is that a molarity? No, I need to turn that into a molarity by dividing by the total volume. What is the total volume? It's 2 liters because we mixed 1 liter, so it's 2 liters. So that is the concentration of chloride. You look for all the sources of chloride that are aqueous. If it's a solid, it's actually not in solution. Okay. Are we good? Okay. All right, best of luck, everybody.